Welcome to day 11 of the advent of compiler optimizations. Today we're going to look at a loop and it's going to show one of my favorite optimizations. So let's have a look in Compiler Explorer. I'm going to start today by writing a routine that counts the number of set bits in an unsigned integer, which sounds like a kind of pointless thing and very unlikely to be useful, but it turns out to be very, very handy for certain packed matrix routines that are used in finance or among other things, and I've used it in games before now. Overall, it's kind of useful, but just bear with me, there's a neat trick coming. So how would we write such a function? Let's just write the signature. Let's do unsigned long. In fact, no, let's use c std int, and we'll use a std uint 64t. Actually, no, we'll just use a std size t to return count set bits for a std uint 64t value. Okay, how do we go about writing such a function? Let's make a std size t count equals 0, or we can actually initialize it nicely like that, and we're going to return count. Okay, we've got our basis here. Now, the general approach that I use is to say, while there are still any bits set at all, i.e. the value is not equal to 0, then there's at least one bit. So let's start with that. So let's say while value count plus plus. And now what I want to do is clear one of the set bits. There's a neat trick to clearing the bottom set bit. I'm going to write it out and then we're going to go through how it works. Value and equals to value minus 1. Let's work through an example. I'm going to pick 1100 in binary. If we subtract 1 from 1100, which is 12, we end up with, well, we know the answer in decimal is 11. What does 11 look like? Well, 11 is 8 plus no ors plus 1, 2, and 1, 1. Let's just make sure that's 3 plus 8 is 11. Yes. So we've got the right answer here. And you'll notice that if we'd have done this sort of longhand using arithmetic methods just by subtracting 1, just like when you're subtracting 1 from a decimal number that ends in a load of zeros, you end up having to borrow from subsequent places up until you hit a value which is high enough to borrow from. So in this instance, what that means is we keep looking up until we find the first 1 bit, and then we borrow from that. That bit becomes 0, and then all of the bits less than that become 1. So this value here is 12, this is 11, and the cool thing is that what we've really done is we've cleared the lowest set bit. This is the lowest set bit. It's now become 0 in the answer, and we've set all of the other bits 1 less than that, but that's unimportant because what we're now going to do is AND them together. And so these bits were 0 before and became 1, but they are still 0. This bit was 1 before and it's 0, so that's still 0. And then every other bit higher than that is unaffected. So we end up with 1, 0, 0, 0, which is equal to 8. And so we've actually cleared this second from bottom bit here. And if you try some other numbers, you'll see that it works for those too. It's a neat little thing, worth doing on pen and paper just to sort of get the gist of it. But rest assured, value and value minus 1 clears the lowest set bit. Let's just quickly go through the routine. We set our output value to be 0. This is equivalent of count equals 0. We're doing a quick check to see whether or not value is equal to 0. And if it is, we jump straight to the end, which just returns count. And then our loop is calculate value minus 1 using an LEA, increment count, and our value with value minus 1, and then jump round if it wasn't equal to 0. Now, the AND instruction sets the 0 flag if the answer of the AND was 0. So this represents a very tight loop that just does exactly what we'd expect. How could we possibly improve on this? It seems like the compiler has generated perfectly optimal code, right? When the compiler is generating code, it has to make some kind of guess as to what CPU it's going to be running on. it usually targets something that is the lowest common denominator of all the current available CPUs. In this instance, for 64-bit, it's somewhere in the region of no Kona, I think was the name of the architecture. But if we tell it that it's targeting something a little bit more modern, and by a little bit more modern, I still mean like 10 years old. If I said, let's use, not no Kona, Westmere. If I use Westmere, we'll see that it generates better code. In fact, our loop has just vanished. So by me telling it that we're using a slightly more up-to-date CPU, and we have to be careful because we need to make sure that whoever is running our code does in fact have a CPU that's at least as old as a Westmere, which is very, very likely in this instance. But the compiler now will generate this much more compact code. And the main part of this code here is this population count instruction. That's right, the entire loop has been replaced with a single instruction. An instruction that was designed to do this exact task, that is to count the number of set bits. That blew my mind when I first saw it. I couldn't genuinely believe that the compiler was smart enough to take my big old loop with all my variables and my while and the little bit manipulation trick, and it recognized that this was in fact the same as one instruction in the output, which is amazing. So compilers can see through quite a lot of things. There's a lot of sophistication inside of them. It's worth noting that these other instructions here, the XOR, the test, and the cmove here, are all working around errata in the CPU. So depending on which CPU we pick up here, let me try Skylake, for example. Let's see what it does for Skylake. Skylake is a much more modern CPU. It still does some other things. So in this instance, it has to handle the fact that when you do a population count and there's no bit set at all, something unusual happened. So here it's using the conditional move to account for that. And then even more surprisingly, the XOR EAX at the beginning here, even though we overwrite EAX with a pop count, there is another errata in the CPU where Skylake erroneously thinks that the population count instruction depends on the previous value of racks. It doesn't, but it slows it down inside the out of order engine. So if we try something newer like Granite Rapids, which is I think one of the later things. How does it change? Yeah, so with Granite Rapids, there is no XOR of racks, which was only there to break the dependency on the previous value of whatever racks was before. Still has to do the cmove to check for 0 bits being set, but it's still faster than looping, which is pretty cool. Just as a side note, we can let's look at how Clang deals with this. Let's do Clang 21. Clang decides that, or Clang doesn't think that we have to use this cmove to deal with the 0 case. I'm not sure why GCC does. I'm not sure either. But one of the more interesting things is we can bring up a window here and we can actually see inside of Clang, if I bring up the LLVM's optimization pipeline, and then if I maximize this, you can sort of see. Here you can see this is Compiler Explorer's internal view of the various optimization passes that go on inside of Clang. And just sort of scrolling down here, what we get is this is the intermediate representation of what Clang has inside when it's parsing the program and optimizing it. Each pass on the left-hand side here is shown up, and any pass that makes a change is a diff. So if I click on this SROA pass, you can see that the code changes between this pass. This is what happened before the pass, this is what happened after the pass. And then I know from experience, if I scroll down this list down here, eventually we find the loop deletion pass, and looking at that output here, it's a bit difficult to see. But on the left-hand side, we can see there's a whole while body, a whole bunch of increments and ands and branches and loop exits and whatever. But on the right-hand side, this deletion pass has deleted the loop, or most of the loop, and instead now we call llvm.ctpop, which is the internal intrinsic to execute the count population instruction on whichever CPU you're on, which is very clever. So you can actually use Compiler Explorer to go digging around inside where the compiler is implemented. If you then Googled for loop deletion pass, you could probably find the code that does this. Hopefully you were as surprised as me that the compiler was able to spot a loop, replacing it completely with a single instruction. I look forward to seeing you tomorrow.